Welcome back, welcome back, welcome back. Of course, we're coming to the end of a very long and eventful chapter. With that being said, I think we covered quite a bit in this entire book. A couple of the big things that keep poking out to us is the Abraham-Lorentz formula, and relativistically, now we have to see the treatment of it. Even with respect to what we saw just the previous question, let's go ahead and see what we have today. The statement reads, the natural relativistic generalization of the Abraham-Lorentz formula would seem to be the Minkowski force 4-vector for the radiation is equal to mu naught q squared over 6 pi c times the derivative of the proper acceleration 4-vector with respect to d tau. This is certainly a 4-vector, and it reduces to the Abraham-Lorentz formula in the non-relativistic limit. But, however, show that nevertheless this is not a possible Minkowski force. And what we showed earlier is the invariant product of the proper acceleration 4 vectors, and we'll see when we dive into this question a little more how this starts to pop up into why this can actually exist. But nonetheless, it's referencing an old question, so we'll have to go pull that up. And for part B, find a correction term that, when added to the right side, removes the objection you raised in A, without affecting the 4-vector characteristic formula of its non-relativistic limit. So again, this Abraham-Lorentz seems to just be a problem coming up again and again and again, but it needs to be handled because radiation theory is quite dense and used in a lot of spots, so it's worth investigating. All right, part A. Well, the reason why is because this is inconsistent with the constraint of that the invariant product of eta with this is 0. And we showed in question 39 how that was. And so we just got to be careful. And these invariant objections, like we've been seeing with the E and B's and a couple other situations, come through to stop what we had thought and really self-correct us. So now what we have to do in part B is, well, we need to find a 4-vector B mu with the property that what we know about how this needs to transform for this constraint is that we need the derivative of alpha mu with respect to d tau plus this constant or this thing beta mu, and what we need to do is when we approach that with the invariant interval, i.e. dotted with eta mu, it needs to equal 0. So our likely candidate guess is, well, so long as we could find something that is a linear combination of the contravariant velocity vector or the proper velocity, where kappa and this parentheses term look to be a constant, then this thing dotted with, or rather the invariant product of the eta mu and the eta mu here should equal 0 based on definitions. That being said, we need to calculate what this might actually look like, so let's plug everything in. But the guess is just a generalization of what we had here for the d alpha mu d tau and then kappa just being a combination or a constant for the combination. So let's look it through, see what we can do. That being said, with this being so, distribute everything, walk it down, we see what should happen. We get the invariant product here, which gives us the negative c there. And so we can kind of scuffle around and see that for it to equal 0, which would be the constraint that we need to see that we have a c squared kappa on the left hand or on the right hand side that needs to be accounted for in the case of, in order for these two things to equal, and we see that that only happens if kappa is equal to 1 over c squared. So our guess to this is to put that we have instead of the d alpha mu over d tau, we have the d alpha mu over d tau plus this constant thing b mu here in the form of 1 over c squared d alpha nu over d tau with the eta mu invariant interval there, or the invariant product. So now we just kind of have to push things and see what else is next. The reason why is because we need to note that eta mu is equal to gamma CV, okay? And this was just how we spelled out the velocity 4 vector. So the spatial components of b mu vanish in the non-relativistic limit, v goes much less than 0. And hence, it still reduces to the Abraham-Lorentz formula. Incidentally, again, this is where we saw in another part of in the chapter where we have the product here is equal to 0, so the derivative should equal 0. So we have a product rule equals 0, and then we solve for one part, and we see that we get the alpha nu, eta nu, and then alpha nu, alpha nu. We like that. So clearly we see that the derivative here is equal to the negative invariant product, and hence b mu can just as well be written as 1 over c squared, where we have the alpha nu times the proper velocity. So again, we have several things working here, several things going back and forth, but this all comes back to the definitions, and the definitions were either established or discussed in problems earlier. So be aware of that. That 1 over c factor seems to be popping up again. And we can also tell that looking at things like the Abraham-Lorentz from chapter 11, we saw that we needed other stuff in there. That wasn't just acceleration. You saw we had velocity terms in there too, so this was kind of expected. But yeah, one more question, and we completed this book. See you at the next one.